Hi, in this model, we will go through the velocity control of a DC motor using a PID controller setup. So on the right hand side, I'm using the same mathematical description of a DC motor where I'm using a velocity actuator as representing a DC motor connected with a spring damper attached with a friction model followed by a transmission gearbox. So the output of the position or the measurement of the torque or the velocity is being taken from here and given to an encoder block who gives an output in terms of counts per revolution. So inside the controller block I have here as this. So this block, attenuate block, it converts the counts into the revolution output, okay, and this is in radians per second. This block converts the output into velocity, and this velocity feedback is given to this plus minus block. So the input here is a motion profile which acts as a set point. So I'm using a velocity output of this motion profile. Subtracted by the feedback, I get an error over here. So this error is given to a PID controller whose output is given to a pendulum output of the DC motor. In between I have a signal emitter who makes sure that the output do not goes beyond a certain range of value plus minus 1. I also take the revolution count output over here, and there is a plus minus block who in turn subtracts the position output of the motion profile with this feedback. So the output of this X error, you will get the positional error of the DC motor. So we would record this velocity feedback in the actual and compare with the reference. To simulate this block, you just press the simulation button and you see these two plots. So here the blue one is your reference velocity and the red one is the followed simulation plot of the DC motor velocity. On the bottom side you see the position reference of the DC motor. Let's download this. So go to Tools, Real-Time Toolbox, C Code Generation, select 20sim template, 4C template, and the velocity controller PID submodel. Click on OK. Select the rotary inverted pendulum setup template. So board should be discovered if you have connected through a LAN network. Click apply and the block goes green. The encoder input we will connect to the motor quadrature counter. The output we will connect to pendulum motor output. Click apply and compile. Once the compilation is over, you can click on command block. So 500 Hertz is the step time or the discrete time interval for execution of the algorithm in the hardware. So we will be logging and commanding at the same time so that we can see what is happening in the hardware. So we can select the variable. I will select the velocity feedback plot. I will select the X error output. I would select the motion profile X and velocity output. So these are the variables I would record and plot in the hardware. So click on apply. So I have the hardware setup here. For safety, I have removed the horizontal arm because I don't want the things to get damaged while the motor spins at high velocity. So you can see the shaft of the DC motor here. So this one. Yep. And I click this button, upload and log. So you can see it rotates clockwise, slows down, and comes back anti-clockwise. So the motor velocity is being plotted in the both directions. So in this simulation plot, we can see the different plots as a reference. So there is a positional error, and here we have. Okay, so that was a motion profile X, but that was not required. So here we can see this plot. So this one, the green one, is the velocity output of the DC motor, which is very closely following the set point velocity. Okay, maybe we can remove these plots and see that again. I just close this. I don't want to see the X because this is coming as much more higher, and the error also. Maybe we can just take the output of this. So we just take the encoder to rev motor output, that is the revolution count, and motion profile X. Let's see how does it behaves. So I can see the motor is rotating on my side. There you are. So here you can see that the pink one is the position set point, and the blue one is the followed one, and the red and green are the velocity plots. So the red one is the set point, whereas the green one is the followed by the DC motor. So here we can see that this guy is following as close as the simulation outputs. Okay, so here you can see side by side performance of both plots. Thank you very much.